Okay, the second speaker is Brad Chamberlain from HPE Enterprise.
Great. Thanks very much. Hi, everyone. I'm Brad Chamberlain from HPE. I'm a distinguished technologist and the technical lead of the Chapel project, which powers Arkouda, which is the main thing I'll be talking to you about today. Arkouda is a framework for doing HPC-scale exploratory data analysis. So what is Arkouda? Basically, think of it in the simplest form as a scalable version of NumPy and Pandas for data scientists. So you as a data scientist are sitting in your Python environment, maybe that's Jupyter, maybe it's Python prompt. You're making what look like familiar NumPy and Pandas calls, but rather than just executing on the desktop like a typical Pandas implementation, what's happening is that the commands are being run out on a server that's in an application written in Chapel. So you can say things like allocate a 10 terabyte array, boom, it's done, fill it with random numbers, sort it, group by, and you're doing all that from the comfort of your Python notebook. Now that server could obviously be written in anything other than Chapel. It could be in C++ and MPI or whatever, but the reasons that Chapel was chosen, which I'll come to in a few slides. Beyond NumPy and Pandas, Arkouda is designed to be extensible, so you can add new capabilities to it over time and have it do other things. I'll talk about that in the next slide. And I think the most important thing is it's just a different way of using supercomputers. So rather than like submitting your job to Slurm, waiting for it to come back, realizing you had a bug, fixing the bug, submitting a new job, you're just interactively driving the supercomputer as you go. And this is really important when you're a data analyst because you want to make a hypothesis, try something out, react to it without sort of losing that human thought loop as you go. So some key properties of Arkouda. It uses a columnar store. So its sort of basic data type is a data frame that uses distributed arrays per column. That said, if data frames aren't of interest to you, as I mentioned, it's extensible. So we've got additions that support multi-dimensional arrays and sparse matrices and things like that. Maybe the most notable extension is NJIT did a graph analytics package called Arachne. It's open source, so it's developed on GitHub and released under the MIT license. It's portable. Basically runs on any system from a laptop to supercomputer. And as I mentioned, it's interactive. So its operations are designed to complete in seconds to small numbers of minutes. Finally, it's scalable. So in practice, it's scaled to hundreds of terabytes, thousands of compute nodes, and over 1 million processor cores. I'll show an example of that here. So one of the key operations in Arkouda that really bogs down a lot of data science is sorting, which is also used by group bys. This is an execution on 8,192 nodes of an HPE Cray EX that sorted 256 terabytes of data in just half a minute. So yeah, this is over 1 million processor cores. And best of all, this is implemented using about 100 lines of Chapel. Somebody transliterated a high-level Nestle radix sort algorithm into this, did a couple more dozen lines of optimization, and that's how we scale to these levels. So one thing to compare against in terms of data frames, obviously, is Pandas. We've been collaborating recently with Oak Ridge to analyze some server telemetry data. They had an existing Pandas script. We converted that over to Arkouda, and on a single node, it outperformed Pandas by about 3.5 times. But then the benefit, of course, is that you can then scale it up to bigger nodes. So this is a weak scaling plot. And the one curve here that's not scaling so well is the I/O, something that we've turned our attention to since taking this data, but I don't have an updated graph here yet. Pandas, of course, maybe isn't all that interesting. Maybe a better point of comparison is Dask and Spark, since they support distributed memory. There's a lot of data here, so I'll say that this is 32 node runs, this is 64 node runs. The x-axis on each is the amount of data, where going to the right is more data. In blue, we see Arkouda, in gold, Dask, and in green, Spark. This is a time graph, so lower is better. And you can see that as the data set sizes, the node counts increase, that the distance between Arkouda and Dask and Spark increases. If we focus on this rightmost column here, which is 4 terabytes on 64 nodes, the workflow that we're studying here is the Mock-Moria workflow, and it has kind of 5 main steps to it. The first one is I/O. The next 2 are kind of fairly simple scalar kinds of applications across the data set. And these are the more complicated sort of sort and group by types of examples. The dotted lines here are essentially sort of this 2-minute interactivity limit that we set kind of arbitrarily. So the goal would be to be under that to sort of keep things interactive and keep the user interacting with their data. And again, the color scheme is Arkouda is blue, Dask is gold, Spark is green. So you can see the I/O in Arkouda was a little bit above our interactivity goal here. As I mentioned, that's something we've been focused on recently. So with some recent improvements, we brought that down below the 2 minutes. We think we can do more to bring it down further, but that's ongoing work. And then if I take the same data and zoom out of it a little bit, so you can see the Dask and Spark lines completely, you can see not only are they much, much slower than the Arkouda when we get up to these kind of scales, but also that there's a lot more variability in their execution times. And I attribute this to the fact that Arkouda is a very imperative in-memory mutable programming model, whereas Dask and Spark are more lazy evaluation, kind of dynamic task graphing types of models. So a lot more variability there. If you'd like more information about Arkouda, the website is a good place to start. And these are hyperlinked. I'll make these slides available to the organizers. There's also an interview with one of the founding co-developers, Bill Roos, that talks about sort of why he did Arkouda, why they did it in Chapel, what worked well, what he might have liked to see improved. So as I mentioned, Arkouda could be written in really anything that scales, doesn't have to be Chapel. Just to tell you a little bit about Chapel, it's a modern parallel programming language. I think it meets a lot of the goals of the previous talk in terms of being higher level and portable and sort of sequentialish semantics a lot of the times. It's portable and scalable, open source and collaborative, and as of just recently, it's been made part of the Linux Foundation through the HPSF effort. The main goals of Chapel are to support general parallel programming and to make parallel programming at scale far more productive. So one way we might look at that is, here are a couple of kernels in MPI plus X. Here's the equivalent code in Chapel. It's much shorter and I would say easier to understand. And yet the performance competes with or beats the reference versions. So why was Arkouda written in Chapel? First of all, because it was productive, led to readable and writable code. And since we were trying to make a system that appealed to Python programmers, we wanted a system where if you had to dive under the hood and add more capabilities, you wouldn't be repulsed by what you saw there, which I think most Python programmers would run away from C++ and MPI. So that was a big draw. Parallelism and distributed arrays are first-class features. That meant a lot to the implementers. Performance was where it needed to be for what they needed. The portability I mentioned before, they did most of their development on a laptop and then scaled to supercomputers. And interoperability, the ability to call out to existing libraries. Beyond Arkouda, Chapel is used for a number of other applications, from simulating the physical world to AI to computer science. So Arkouda is one of our killer apps, but not the only one. And if you'd like to learn more about Chapel, a good way to learn about some of these applications is through this series we've been doing, 7 questions with Chapel users, where we ask them about what are they doing and how's Chapel helping them. So that's a good way to learn more about these applications. If you'd like to engage with us, we've got synchronous live weekly meetings you can join, various ways to keep in touch with the community, including social media and various discussion forums. And I will end here. I'm out of time. Thanks very much.